Hello, and welcome to this tutorial on algebraic expressions and equations. We've actually seen several algebraic expressions in the earlier tutorials. And looking here, what you'll see is, for example, the present value of future cash flow discounted at rate R. This is related to converting an annual rate to a semi-annual rate. This is related to converting a money market rate to a bond equivalent annual rate. And this is related to the problem where we had a series of annual returns on a portfolio, and we wanted the average rate over the full period. And algebraic equations are essentially taking an algebraic expression and setting it equal to either a variable or another expression. So here we see it specifically stated: the future value of some investment P invested at a rate R for n periods is represented by this equation. This represents the equivalence between the return on getting a semi-annual rate paid twice a year versus an annual rate once a year. This represents the equivalent that you would have at the end of a period for a money market instrument versus a bond compounding at an annual rate. And then this represents what you would have at the end of 3 years from, say, your equity portfolio, and this is what you're trying to get at, the average over 3 years. So these equations basically express either identities or desired relationships that you're trying to achieve. So let's look at an example of how we would use this. So with an equation, you can manipulate them and essentially solve for one variable by doing equal operations to each side, so essentially maintaining the equation. So for example, let's look at the equation that shows the amount that we would have principal and interest after a year for investing at a semi-annual rate. So that's half the semi-annual rate paid twice, so it's then compounded. And this is what we would have at the end of the year versus if we had just invested at the annual rate and only had one compounding. And so in this case, what we want to know is, let's say we know RA and we want to solve for RSA. And so how do we do that? Well, we'd like to come up with an equation that has RSA on the left-hand side and equals to something, some formula on the right-hand side. So what we have to do is we have to do a series of operations on each side. So the first thing we have to do is essentially take the square root or the half power of each side. So by taking the half power of this side, we're essentially multiplying that by 1/2, and then this becomes 1. So the exponent goes away, but then taking the half power of this side puts it there. So this would be maintaining the equation. And then we subtract 1 from each side. So -1 from here, it disappears, and then we have -1 over here. Okay. And then finally, we multiply each side by 2. So 2 on this side cancels out with there, but then we have a 2 here. And then you have to be careful that it's going to be the entire amount. So you need to put a brackets to represent that. So this is how you would, from this fundamental relationship, derive the formula for getting the semi-annual equivalent rate to some annual rate. Now, another important algebraic expression used in finance is the weighted sum. But let's first look at the sum and make sure we're comfortable with the terminology. So you'll see this, it's called a sigma, n equals 1 to n, x subscript n. So basically what this means is x1 plus x2 plus x3 on out to xn. And so, for example, if we had 3, capital N was 3, so we would have x1, x2, x3, and they took these values, then this equation would mean this. It would mean we're adding 30 plus 25 plus 50, and that would equal 105. So that's the simple unweighted sum. And we'll of course, use those as well in finance. But the weighted sum is a little more complicated, but also very important. And so here what we're doing is we're taking some variable wn and multiplying it by xn. And there could actually be more than one variable here, but we'll just look at two. So essentially, we're taking the sum of the products of these two variables. And so in this case, let's say we have the same xn's as we had before, but we have these wn's. You can think of them as weights. So 2 for the first, 3 for the second, and 0.5 for the third. So essentially, we're saying take 2 times 30 plus 3 times 25 plus 0.5 times 50. And that's what this means. So to put this numerically, we would say it's equal to 2 times 30 plus 3 times 25 plus 0.5 times 50 equals 160. And then we would do that on our calculator as follows, and you would get the same result. Okay, so let's look at a specific finance application, which might be just to calculate the total portfolio value of a bond portfolio. It could be a stock portfolio as well, but we'll look here at a bond portfolio. And let's suppose we have these three bonds, and they have face values, and then they have prices. And the prices are percent of face, so we have to be careful with here. This is 106%, not 106. And so we want to basically calculate the entire market value of the portfolio. So this is the calculator keys we do. We take the 300,000 times, well, 106% is 1.06 times that, and we get 318,000. 100,000, and then add to that 100,000 times 1.02. That brings the cumulative total to 420, and then add 200,000 times 0.95, representing this 95%, and we get 610,000, meaning the portfolio market value then is 610,000. Now, another statistic you might need to calculate would be the average maturity of the portfolio. And let's suppose that we are going to do that based on market value weights. It could be on different schemes, but we're going to do it based on market value weights. And let's say the maturities are given here. And so it's essentially the same operation we did before. We're going to take 52%, 0.52 times 5 plus, and 0.17 times 8 plus 0.31 times 11 plus. So essentially we're taking each of these, multiplying it, and then adding it to the next. And we'll get to 7.37, which would indicate, based on this weighting scheme, the portfolio average maturity would be 7.37. Now, I should maybe caution you here, and many of these problems we see percent. And you might notice there's a percent key on your calculator, and you also notice I've studiously avoided using it. It sometimes doesn't work as you expect. And so maybe I'll just leave it at that and say, unless you're really sure how it's going to work in a specific instance, it's much safer just to use the 0.52. In this case, for example, it would not work. It would give you the incorrect answer if you were to have typed 52% times 5 and then added it. So let's summarize. Algebraic expressions represent calculations with variables. So for example, this one here that we were looking at, algebraic equations represent the equivalence between one expression and another, such as this. The equations may be manipulated by doing identical operations on each side, and this is done to solve for a variable of interest. So this could be taking the same square root, or taking each side to the same power. It could be subtracting or adding a number to each side. It could be to multiply or divide by the same number. So as long as you're doing identical operations on each side, you maintain the equivalence of the equation. And you will do that in order to isolate one variable on the left-hand side and get a formula, typically. Weighted sums are a special type of algebraic expression used often in finance in the analysis of portfolios, and you will see this kind of notation with sigmas and subscripts, so get comfortable with that. For more review of algebraic expressions and equations, I would encourage you to check out these two links. The first one deals with expressions specifically, and the second one deals with equations. It goes on beyond quiz 2, so I would recommend you just go through quiz 2 to cover the material that was covered in this topic, and do these particularly if you're uncomfortable. The second one, if you're uncomfortable with manipulating equations, maintaining the equivalence, so that you become very comfortable with that. So that's it. Thank you for listening.